Hi everyone. In this tutorial session we'll be looking at a basic Cellular Automata script that we will construct in processing. And for this exercise I'll quickly introduce you why we are looking at Cellular Automaton. Cellular Automaton can model cellular complexity using binary rules, and we are actually going to look at some of the functionality with one-dimensional and two-dimensional arrays. So to begin with, here you're looking at actually how basic computation for a sequence of data is structured. So if we have a string of values, or these could be binary values, then basically we are actually looking at triplets of data, and using this key here, we are actually determining the next generation for this sequence. And because there are 8 possible rules, there are 256 options for the Cellular Automaton. So if I go to rule 30, you're seeing the manifestation of rule 30 starting from a single cell here that is active and marked as black. And you're seeing how the progression for this algorithm runs. And there are also other rules like rule 90 that is generating more like interesting behavior, and rule 110 as well. So we'll be looking at some of these, and we're going to code kind of a basic way of how this algorithm could be run. So I'm going to first show you the completed version of the algorithm and then explain you how we're going to build it in steps. So when I run this code, you're looking at kind of the initial seed that we're going to start with. This is randomly generated. And for the black dots, you're actually looking at active cells, and the white cells will be inactive. And when I run the simulation, you're actually seeing how the progression for this algorithm is run. And we are actually doing, in this case, rule 30, which is linked here. But changing these true and false values, you can actually customize how this algorithm can output different values as well, or different images. Now the first thing I'm going to do is start a new sketch, and I'll be overlaying this on top of that. And we're actually going to start with defining our first two functions. So the first two functions we need are void setup, and I also need a void draw. So inside of here, we're going to define kind of a size for our simulation. So I'm going to define 600 by 600 pixels. And I want the background to be 255, which is white. For this exercise, I actually wanted to define a resolution for the cells. So let's call that dimension, or short for dim. And I'm going to give 5 pixel dimension for each cell. And I'm going to work with a Boolean list here. So Boolean array, let's call it Cellular Automata. And this will be a global list that we are going to change and control. And it's going to store the current Cellular Automata values for any rows that we're going to generate. And to keep track of the rows, I'm going to define a function called y, a variable called y, and I'm going to start with the 0 value for y. Now inside of setup, I need to determine or initialize my list. So I'm going to type up Cellular Automata as new Boolean, and I want to state that I want the length of this array to be calculated according to the resolution. So if my width is 600, I divide it by resolution of 5, and I'm going to get basically 120 cells per row. And if I, let's say, change this to 10, then I'll have 60 in this array. So I'll be keeping a list of 60 variables inside of this array. And we're going to first randomize the values inside of this list. So I'm going to write here randomize values for the first generation. So how do I do that? I write a for loop. So for int I equals 0, I want to go through the list, I smaller than ca.length and I plus plus. So this will go through the list regardless of what its length is. So if my dimension is 10, width is 600 pixels, I'll have 60. So this will go all the way up to 60. So it's going to start with 0 and it will end up at 59. And inside of here, I'm going to check if, basically, I want to throw a random variable. If random1, or you can just call random smaller than 0.5, so there's a 50% chance that our variable is going to be true or false. And I'm going to assert, basically, I'm going to write false, or I'm going to type up true. So there are different ways of specifying this in a single line, but I'm making this example as extended as possible so that we can actually see kind of the basic coding in processing as well. Then I'm going to call a function called show cellular automata so that we can visualize what the current state of the cells are. I'm not going to write anything under draw function yet, so let's look at what we're going to say in show cellular automata. So I've defined show cellular automata function. We don't need any input here. And inside of this, basically what I want to do is go through the list and visualize the cells. So I can simply copy this for loop here and paste it. And what I want to do is, rather than checking with a random variable, I want to check the state of the cell because we already assigned it something. So if it's true, I want to do something here. Basically, I want to, let's say, define no fill and stroke as 255. Or we can actually make it the other way. So if basically it's true, I want it to be a fill. So let's make it fill 0. Let's visualize the active cells and stroke 0. Whereas if the cell is dead, so this is the alive case and this is the dead case, I don't want to be any fill, so I'm going to type up no fill. And I want the stroke to be 255, which is white. And after specifying the colors for the cells, then we can go ahead and place a rectangle there. So the rectangle is going to be I times dim y, dim minus 1, and dim minus 1. So basically, this will generate this will represent the first row of our cells. So when I run this sketch now, you can see that we get the first random generation here. So on top, you're actually not seeing the dead cells. So if you want to see the dead cells, we are not putting any fill, and we are stroking it with with white. So if I change it to black as well and run the sketch, you can actually see the white cells are also there, but we are not showing them. And just for clarity, we can actually do no stroke here as well, so it's actually the same thing. Rather than painting white, we don't have to paint anything. So we can also control now the size of this array. So if I make it 20, we're going to have 30 cells. And if I make it lower, let's say 5, we're going to have more cells. So again, the pixel dimension is 600. So when I divide by 5, I'm actually getting the number of cells in a row. and our default y value is 0. So that specifies the first, if you remember the sketch, on the left top corner it's 0, 0, and bottom right it's 600 by 600. So when I specify y as 0, I start from the left top to draw, so that each rectangle is drawn first using y value as 0. And that rectangle is being specified here. So when y is 0, we're specifying here. So what I'm going to do is, when I calculate next generation, I'm going to increment y value with dimension so that we can start drawing in the second row. And to do that, let's actually switch to the next generation function. So I'm going to type up void nextgen, which is for next generation. So we want to calculate, what we want to do is basically define a new array here and use the CA function, CA list, to calculate the new list and overwrite CA with the new generated list. And we have to apply some Cellular Automata rules here. So first thing, I want to define a new Boolean list, which is going to be CA next equals new Boolean. And this is going to be width divided by dimension. And then I want to go through all the cells in this list. So again, we can copy this line. So I want to go through the CA list. And the way we're going to do this is by checking triplets. So I want to, basically for the current state, I want to look at its left and its right and its current state. And those triplets are going to be used to determine what the next generation is. So if I have, let's say, in this case, you're seeing the animation, if all of them are true, the next generation is going to be false. So if the left one is false, right one is false, but the current state is true, then we're going to have the next generation as true. So to check for the triplets, I basically need to find the left, right, and center. So I'm going to type in Boolean left equals, so I want to access that from the Cellular Automata list. I'm going to type in I-1, which is the index for the left cell, plus ca.length, and mod ca.length. So what this does is basically, if, let's say, my index is 0, I won't have any left cells. So when I'm checking for this index, I want to check for the last index. So to convert those, I basically subtract 1, which makes this -1 if I is 0. Then I add the total length of the Cellular Automata list. Let's say it's 20, then it makes 19. And I'm also taking a mod here, which may not be necessary, but when you have I as incremented, then this formula is going to get past the total length of the CA. So then you need to take a mod so that you can have the remainder, give you the current or the right index. And for the current state, it's pretty straightforward. So when I say I want to look at the current cell state, I can simply say CA, CA, and open brackets and check for the I index. And then I'm going to check for the right cell, which is going to be I+1 and mod ca.length, so that when we are past the, so again, similarly, if I'm checking for the last index and I add +1, I'm always going to exceed the current length of the list. So let's say if I'm checking for index 19 and I added +1, it's now 20. And if I mod it with 19, I'm going to have, if I'm at 19, I'm going to add 1, so it's going to be 20. And if I mod it with 20, I'm going to have the remainder as 0, so it's going to give me the first index on the list. And using these, we can simply go down and apply the rule 30, which is if left. So we can start checking with the left. So we're going to have a lot of nested conditionals here. and I'm going to check else. So if left is basically true or false, then I can simply check if center is true or false. And then here I can check if right is true or false, right? So I'm simply checking, passing in the variable because it's only stores true or false. So if this is true, it will go inside the if statement. If not, it will pass it. So if I'm here, then the condition is 1, 1, 1. So all of them are true, or you can say true, true, true. CA next, we want to specify at the same index false, and this is for rule 30. So I'm going to write up here rule 30. And how can we check for that? So if you go back here to Cellular Automata, rule 30. So what did I check for? I checked for left, center, and right being true. So if I go all the way down, there should be a rule set. Here it is. So if all of them are true, 1, 1, 1, my next statement is next generation is going to be false. Now if I type in an else here, keep in mind that I checked for right. So if all of them are true, this is 1, 1, 1. So here only right will be false, so it will be 1, 1, 0. And that is also false, so I can make a copy of this and put it here. Now we checked for center being true, and I can simply specify an else statement here and make a copy of this section so that inside center will be false now. So right will be true, left is always true. So I'm checking with 100, 101, which is false, and 100, which is 1. So this will be true. And you can simply make a copy of all of these and paste it here as well in an indentation. And for these, the left will be false now. So if I just changed the first letter to 0. So 0, 1, 1 is true. So I'll type in true here. 0, 1, 0 is true as well. 0, 0, 1 is true, and all the zeros, they are false. So I'm also checking here, so you can see that I applied the same rule. And in the final step, we basically went through the for loop, closed the if statement, and I'm simply going to close the for loop as well. And all I have to do is override the old CA. So CA equals CA next. And I want to increment y by dimension so that we can move to the next row. And I want to do call the show function here. So every time I call next generation, so the first generation will be automatically visualized. Every time I call next generation, we are going to compute it, overwrite the old one, increment y, and show it. So we should have a way of calling this next generation. And the way I thought about it is basically we can define a Boolean parameter here. Let's call it Boolean active and start it with false. And down here we can type in void key pressed. And if I press any key, I want active to be not active. So basically, if this is false, it will become true. So because not active, not false is true, so it will become active. And inside of draw, I can simply say if active. First, we want to check if the simulation is active. Then inside of here, I want to basically call next generation function. But we don't want to call next generation every second of the way. So I want to basically type in a statement for the speed of the simulation. So let's say if frame count mod 24 equals 0, which will basically say like if our frames are updated 24 frames per second. So this means this is basically going to represent a second. So we want to generate each row every second. You can also, if you decrease this value, it's going to be a lot faster. If you increase this value, it's going to be a lot slower. Then inside of here, all I want to do is call next generation. So let's run our function. And inside of here, I'm just going to press one key, and you can see that every second we're getting a new row being displayed. So if I want to increase the speed, I'm going to decrease the frame count mod function, and now it will run a lot faster. And if I want to change the resolution, let's make it a lot finer, and let's make it a lot faster as well. So you can see I'm printing the data. And if you want to generate a different rule, let's say we don't want to generate rule 30, but we want to generate something else. And for that, you need to find a rule that interests you. So let's go to rule 184. This is actually going to give diagonal lines. So let's see if we can find something a bit more interesting. You can also go back to Wolfram's rules. Let's look at rule 90. So this is rule 90. Let's try it. 111 is false. 110 is true. So I need to type this up as true. This is false, and this is true. This is true, false, true, false. So I need to change only these two rules. And now let's run it. And this will be printing a different visualization. So again, each row is affecting how next row is generated, and we are visualizing it like a simulation. And I can increase the resolution here and the speed. And I can change the rules and plot 256 different variations. I made the input random as a sequence, but you can also start it from one point in the middle and then make it branching as well. So I hope you liked this video. Thanks for watching.